My name's Dave Lacey, and I'm going to talk today about computers for the age of machine intelligence. Now, what I'm going to do is I'm going to go over really two trends that have really grown immensely in the last 10 years. They're not just 10 years old, but the last 10 years have really seen extreme growth in these areas. And that's accelerated computing and machine learning and the software development tools associated with machine learning. And I think this is an excellent thing to talk about because over the next 10 years, I would expect these to grow even more in their applicability and really to pervade into almost every aspect of computing. So if you're a computing practitioner in almost any area, you would probably expect to see either both machine learning techniques and accelerated computing techniques kind of entering in some form into your work. As said, my name is David Lacey. I've been working for quite a long time now in compilers and programming languages, development environments of various forms, both in research and development, often working on top of new architectures. I've also worked in various other software areas, high performance computing, finance, embedded computing, signal processing, etc. So software is really my thing. I'll be talking about both software and hardware today because it's a combination of those two things that is one of the things that makes this field very exciting. Where I'm doing that at the moment is at a company called Graphcore. We were founded in 2016, particularly to target this new area of machine learning and machine intelligence. And we are doing that for both training and inference workloads at large scale on the IPU. Now, the IPU is a new processor, the intelligence processing unit that we've made from scratch, particularly for this machine learning area. We've grown a whole company to support that. And that's the kind of position I'm talking from today and the experience I can give. To give you an overview of this area, we're UK based, our headquarters is in Bristol, but we now have over 600 people around the world with offices in Norway and in Palo Alto, Beijing. Really, we are a worldwide endeavor doing this quite complex work to produce the kind of systems that you need for this area. I'll talk a bit more about those later on. Okay, so what am I going to talk about? Firstly, I'm going to talk about this idea of accelerated computing, about using heterogeneous compute and accelerators to tackle the workload you're interested in and to get high compute power. Then I'm going to talk about machine learning, its rise, and how it's given rise to new ways of developing software and what that means for software developers. And I'm going to talk about, particularly from the system hardware level, what's going to happen in the future, in the next 10 years, how will our systems evolve to tackle this real need for compute in the machine learning world. But let's start with accelerated compute. Now, this is when you have a model particularly in scientific and engineering applications, where calculations you have a main processor which does general purpose compute, and then you have specialized computers that work in tandem with them to do specialized high performance compute, and these are known as accelerators. This is not a new idea. I think people of a certain age might remember x87 floating point coprocessors in the early days of CPU desktop and server systems. But it's really kind of grown into a major component of any computing system nowadays. We can see the history a bit here of the top 500 accelerated high performance computing systems. Now, for those that don't know, the HPC community have a standard benchmark competition every year, top 500 running a linear algebra application, and there are variations as well. And this shows the mix of in those systems of the kind of accelerators that you get in those systems nowadays. Now, you see, if you go back to 2005, so about 17 years ago, there was nothing in terms of accelerated computing. And then in 2006, the first accelerated system of this nature was at the Tokyo Institute of Technology, with a system that had both CPUs, had about 200 and something nodes, I can't remember exactly, and reached about 50 teraflops at that time, so things have moved on quite a bit. But importantly, had accelerators there, had these clear speed SX600 accelerators, ClearSpeed was actually a company I was involved with in Bristol at the time. It was another UK-based company, and it was the first time that accelerators had got in that competition. Interestingly, at the time, there's a question about whether they should even be allowed in this benchmarking competition, which seems kind of odd now, but at the time, although you have to think that benchmarks and competitions need to represent typical use, and there's a question, is this typical use to have these hybrid systems? But then as you see over time, you can see there are other accelerators came in, the Sony Cell system, ATI, which then merged with AMD later on. And then you can see from about 2011 onwards, these became really dominant in the competition, that every system for HPC had GPU accelerators inside them, and mostly NVIDIA GPU accelerators. And this really has set a trend, and it really does represent typical use nowadays in high performance computing. Many workloads, probably the majority of workloads, will be worked on with accelerated hybrid systems of this nature. So that is really the growth in this idea that to do certain tasks you need different types of machine working together. And then in the same kind of time frame, there's been a growth in the new domain of machine learning. And we can go back to about the same kind of time that spike was happening in accelerated HPC systems, that we started seeing accelerated machine learning. So this is taking machine learning systems, particularly deep learning, and using accelerated processors to increase the compute capability of those machine learning systems incredibly by several orders of magnitude. And really, is one of the kind of key points that I've highlighted here is a paper in 2012 which released AlexNet, which was a system, a neural network, a deep neural network for image classification. It took ImageNet data set and classified the images into different types. And there are a couple of notable things about this submission. Firstly, it was a real step up in accuracy in that benchmark. It really launched a real interest in how much deep learning systems can do. It didn't really do any feature engineering, just took raw pixels as input and outputted the classification, learned everything in between. And crucially, it was also implemented using GPUs, generally programmable GPUs, to execute the system. It used tGPUs to calculate it during its training run, where it would take in a load of data and work out the learned parameters of the deep neural network that could classify these images. And that really, you could say, was really the launching point. It might not be the very first accelerated, but it's certainly one of the most significant accelerated deep learning algorithms that kind of led to this explosion in machine learning. Okay, if we fast forward now, 10 years later, and we can see that machine learning systems, accelerated machine learning systems, have really evolved. And to use an example, I'm going to use our own Graphcore Bo 2000 Pod 16 servers. And here we can see that it's not just a couple of GPUs in a single machine. We have a multi rack system with a 5U module made up of a head node which contains a CPU, and four, in this Pod 16 configuration, four Bo 2000 modules, each of which has four of our processors on, and critically have a specialized interconnect between them. So when all these chips are working together, information can be passed around very efficiently, and we can get even more compute capability by scaling up, by adding more chips into the system. The Bo machine there, you can see on the bottom right now, there gets 1.4 petaflops of AI compute in a single 1U rack. So we're talking about a very, very high level of compute density here that's being used. The processors in there, again, as an aside on the technology increase there, we've done the first wafer-on-wafer die stack in that processor. So we're beginning to build 3D chips on top of each other just to increase the compute capacity. And this leads us to a kind of new class of machines, a new world for doing this kind of workload. That example I explained in 2012 took 6 days to train to determine what the learned parameters should be given the data set. And today, that could be done on one of these systems in minutes. You can see the Pod 16 system, which I just showed, would train a similar network. Actually, these are ResNet50 numbers, which are actually get better image classification. It's a slightly different network structure. It gets better image classification. Performance than AlexNet. It's actually slightly fewer operations as well. So it's not just compute innovations, it's algorithm innovations here as well. But it's mostly compute. It's mostly the fact that we've packed more compute into a smaller space. And that Pod 16 system will do this in just under 20 minutes. And then you can scale this up. If you took one of our larger Pod 256 systems, it would do it in 2.57 minutes, do the training run, equivalent to that 6-day run in 2012. So in 10 years, that's reducing a training time from 6 days to just under 3 minutes. So that's the level of innovation we've had both in software and in hardware and in scale to enable these kind of systems. And that what enables these kind of systems to start to invade every class of computing and many different use cases. And really, when we kind of look at those use cases, we're actually seeing arguably a new programming paradigm. On this slide, I've got an example here from the GitHub Copilot service, which is a really interesting service in many ways. It's one of the first applications of neural networks of the size and scale of the underlying network that it uses with lots of compute for a very interesting application for aiding computer programming. And if you see on the left here, if you were 10, 20 years ago looking at the task of programming a system to say, given a programmer writing a program, give them hints on how to complete that program, you'd do that by trying to break down the problem, trying to write, kind of decompose it functionally, work out how we could get good software architecture for this structure and produce that kind of work, and it probably wouldn't work very well. But today, that's not the programming development paradigm we're going to use. We're going to actually train a model to understand the key logic, and then we have to integrate that into a standard workflow for software development. What's interesting about this is it also shows the other side of the coin, which is that machine learning is also going to start to affect the way we do traditional software development as well. And Copilot is really probably just the start of that, the start of how machine learning assistants can help with coding. This does code completion, but if you think about all the other aspects of software engineering, probably most of those can also be aided by machine intelligence to create programs. So we have both a new paradigm in integrating machine learning systems into our software development, and also a new paradigm of software development where machine learning systems help us. So that's kind of really quite exciting. But I'm going to concentrate on that first bit. How do we get machine learning into our software development flows? And I think what's really been key to this that we've seen, again, over a similar kind of time period, the last 10 years, is the rise of new programming frameworks to do this. Most of these tend to be Python-based. They're not, some of them are multi-language, but actually the programming language is not the key thing here. It's really what's being represented by the framework in that programming language, what's embedded in there, how it represents the learning structure as a compute graph, how it deals with the machine learning optimizer that's going to work out what the parameters are of that compute graph that you've created, and so on. So it started off quite early in universities. We had Cafe Theano in China from the US and Korea, respectively, universities. They were the kind of first wave. I think people learned a lot from those. And then as the kind of got this explosion in use over time, A whole load of new ones came along around about the 2014-2015 time, and particularly I'm going to really point out TensorFlow and PyTorch in there, two very kind of key frameworks that I'll talk about in a couple of slides. TensorFlow has evolved. I think it had a very big revision about 4 years ago, and TensorFlow 2 works in a very different way. It's integrated Keras into that framework. And I don't think this evolution has stopped. We're seeing new ones emerging. Julia, which is a general purpose programming language, but also can be used to accurately kind of represent the kind of compute that we're doing in this field, and JAX, which is built on top of initially built on top of the same compiler backend as TensorFlow, but has a very different kind of paradigm of coding at the top, which is emphasizes a bit more in terms of flexibility, even if you have to do a bit more explicit work, is also becoming very popular as well. So we have quite a growing, a bit like the programming language evolution that we've seen traditionally in software. We're also seeing at the programming language framework level for machine learning. They all have very similar abstractions. That there are different ways you can create the graph, and when the compiler or the system has a view of the whole graph. I won't go into those details. There are differences, like the difference between eager and execution and ahead of time graph compilation. But generally, they all work with computation graph. That is good to have as an explicit representation, because then you can differentiate it, so you can apply a transformation to it to work out how it's going to behave as we evolve it in optimization for machine learning. That then gives you a load of operations and their dependencies that you have to execute. So there needs to be a scheduling phase, and then that will boil down to processor execution. So there are common abstractions you see here in compute graphs that you see across all the frameworks, which we kind of embed into the lower levels of our stack to support these frameworks well. And as I mentioned before, PyTorch and TensorFlow have really become the dominant for today industry standard machine learning frameworks. They are PyTorch was designed and built by Facebook, and actually has been supported by quite a large open source community. It's had a very high level of input from various places as a genuine community project. And it's built around what you call an imperative programming model, sometimes called an eager programming model, where when you execute a line of code, that line is dispatched, the operation is dispatched to the computer to be executed straight away. TensorFlow was designed and built by Google, again supported by a large open source community project, though I would say that Google had very much been the key contributors there. And that's built around what you call a declarative model. Again, you describe the whole graph beforehand, before it's executed. So even in the high level user program, not just in the compiler, you have a full graph representation that you're building. But as these have evolved, I think those differences are going away a bit more as these evolve, and you'll see in the later versions of PyTorch and TensorFlow less of this difference, certainly. And but definitely these are the two that are used the most. Okay, underneath all this, you need an SDK, not just the Python interpreter on the host, that will take whatever those frameworks are describing in their compute, and translates it to run efficiently, not just on a single chip, but on several chips, all communicating together, maybe across several different racks in a data center with networking between them, and so on. Our stack is a description of this. I've just put it as an example. I think there are several others there, and generally you'll find that different vendors of machine learning hardware will provide different stacks, but you get the commonality of code at the top because they're all coded up in these frameworks. Underneath that, you need several things. You need various levels of compilers, because you take that compute graph and it will compile down not to machine code but to a lower level representation, and then we're going to distribute that onto multiple cores and multiple machines, they're going to need compilers to then take the task they've been given and effectively reduce it down to binary code to run on that individual machine. They're going to need to link into high performance libraries, hand optimized libraries for common operations. And then the communication between those all has to be marshaled and implemented efficiently. And on top of that, you need the standard support for debugging, security, reliability, and so on, and everything you need to effectively run large-scale programs. So there's a lot of work needs to go into the stack. For any vendor like us, we also like to provide many kind of tutorials and examples and so on to users on how to use these systems. If people are interested, this is my time to plug to go to the Graphcore website and go to the developer page where you can see lots of information about how to develop our hardware. On top of those frameworks and stack, there is a bigger, what you could call application level ecosystem of to help developers develop the world. And this is what really is going to lead to people being able to use machine learning in many, many different projects. So we have things like Hugging Face, which is producing boxed up machine learning models that are well tested, well conditioned, configurable, easy to slot into your application. Those kind of things at the application level, so you can just go and pick and choose what machine learning model you want. We've got things like weight and biases, providing visualization and data logging techniques to, as you're running lots of experiments, to try and do some machine learning that you can visualize what's going on and sort all your data. Things like PyTorch geometric are domain specific. This PyTorch geometric is for graph neural networks, domain specific libraries that allow you to develop particular types of neural networks. And then on top of that, we have kind of pipeline, ML pipeline, plug and play style applications like Gradient from Paperspace that is really no code solutions for plugging together existing components to give you a machine learning pipeline. If you're trying to use existing kind of work to just put some machine learning into a microservice application on a server, for example, things like that. And all of those things are growing and developing, and we'll see more of this over the next 10 years to really target lots of different applications. And there are more and more applications that this will target. We're seeing, as well as I said initially, there's a lot about language understanding and image recognition, but there are applications of this in finance, to time series data. Biotech is a really big growing field in machine learning, things like drug discovery and other areas as well. There often we have, I mentioned graph neural networks with PyTorch geometric. That often comes up in the biotech world. In scientific research, accelerated computing has been used a lot there for simulation in scientific research, but we're seeing a lot now of co-simulation, where you're doing some physical simulation of a system coupled with a learned model of some phenomenon, and then the two interacting. That's a really big area that will really improve our scientific research. And clearly in consumer internet, understanding images, understanding language, understanding video, understanding user intent, these are all things that are massive applications for this kind of technology. Okay, so that kind of gives an overview of both hardware and software development trends over the last 10 years or so. That kind of hopefully gives people an idea of where we are with this machine learning world and what the potential is there. But going forward, what's the future? What's possible in this world? And it's very hard to tell. I haven't got a crystal ball, but I'll try and give some points that might point towards it. First one is on hardware. If we look back at the compute scale up, so I said, like going from training in 6 days to under 3 minutes, that's been done via various ways. We look at various ways. If we look at GPUs, for example, we've got a 300x speed up in the last 10 years. How have they done that? Well, part of that is by architectural, being arranging things well in your digital architecture for this application. Part of that is clock speed via Moore's law and Dennard scaling and so on. So that's transistor density as well, means we can fit more on a single chip. And part of that is from moving from, if you like, vector computation to matrix computation, where you can amortize certain overheads within a chip, and that gives us a speed up as well. So all these things combined together has kind of given us this big speed up. How far can we go with that? Well, in the next 10 years. Oh, sorry, that is waking up. Well, we should be able to get somewhere with hardware improvements. The matrix multiplication, maybe we could make bigger and bigger systolic arrays, but we'll get diminishing returns from those. There are physical limits on how far we can go transistor latency and so on. So there's a limit to how much we can push compute over the next decade. So we shouldn't expect necessarily the same kind of increases we've had in the last decade or the 2 decades before that in raw compute power. So what can we do? Well, we're still going to need a lot of compute because we're going to need a lot of intelligent capability, and that really has been shown to come. There's lots of research to say that comes with scale, and by scale I mean having more parameters, more variables in your model that can model more and more intelligence about the world, and then you have to throw more and more data at it to allow it to learn. Now, at the moment we are talking about multi-billion parameter models. As we increase from 8 billion to 62 billion to 540 billion now, the latest like Palm Pathways model, you can see more and more capabilities coming, and this will keep going. So we expect to be going into the trillions of parameters, but we have that limitation on compute that we had before. So the question is, if we're going to move to larger and larger models, and we're going to be limited on how much we can push the compute of an individual chip, where do we go? Well, there are 2 things we can do. We can either work with scale. We can make bigger and bigger computers. That's fine if we can power them. And we can also work with sparsity or selective execution, or basically just being more clever with our algorithm and doing less compute per parameter for the same effect. So we need to be able to support those kind of algorithmic extensions, as well as providing more and more capable hardware to push the bleeding edge of where we can go. So at Graphcore, we're committed to doing both of these things. We have committed over the next few years to build a 10 exaflop machine with 8,000 IPUs, next generation IPUs in. And this machine particularly concentrates on 2 aspects. One is scaling capacity, so having 4 petabytes of memory in it to allow really big models, and also scaling the ability to do clever algorithms that can use those parameters even with the compute per node being, say, 2 or 3 times what it is today. Now, that won't be enough just to brute force everything. You need good data communications, and so what's important is the bandwidth, the memory, and the flexibility of communications between these nodes. So the Graphcore Good Computer plan is to build something that big, but also be able to make something where practitioners can really use this for effective machine learning in the future. Okay, so in conclusion, we've had a lot of progress over the last 10 years. Expect the 10 years coming to have even more progress and even more usage in many, many areas of computing. We are getting to the point through programming frameworks and the levels above, the application level frameworks, the plug and play, zero code solutions, all this kind of stuff. That means we're getting more standard software tools and practice for actually using it, even if you're not a machine learning expert. But it's emerging. There's a lot more to come. I think over the next 10 years, we'll see a lot more maturation in that area. and those tools really becoming very effective, and workflows becoming much more efficient. At the silicon level, at the individual chip level, scaling, if you think of it from a hardware point of view and energy per operation, is getting near the end, right? There's a physical limit to how much we can do. But we can still go bigger and bigger. Multi-trillion parameter dense neural network models aren't feasible if we just do it in the brute force way we do now, but are feasible with algorithmic innovation and the systems to back that up in terms of flexible communication, large capacity memories, etc. So hopefully that gives an idea, at least a kind of small bit of insight into what happens in the next 10 years. I'm not entirely sure, but I'm very excited to find out.